Okay, so it's a great pleasure to have Spenta, who's agreed to give this, tell us about black hole evaporation.
Thank you. Can you hear me? Am I audible?
Yes, sir.
Thanks. I'm going to tell you a little bit about some work which we have done over the last couple of years with Gaikwad and Kaushal, who were then students, now postdocs, and with Gautam Mandal, TIFR Mumbai. So my talk will basically be about trying to understand black hole evaporation in a dynamical sense, especially trying to understand the end point of evaporation, which carries a lot of fluctuations. We worked in what I would like to call the Ising model of black hole physics, in the sense that we all know historically how important the Ising model was for the theory of critical phenomena. And the SYK model, SYK stands for Sachdev-Ye-Kitaev. So let us look at the quantum mechanics of a model of n real fermions, okay? Interacting in groups of 4 or less. I'm sure in this audience, you must be knowing about the SYK model. Now this all-to-all interaction actually is very fundamental because it leads to a highly entangled many-body state, which is precisely the type of physics we need to understand black holes and their microstates, etc. Okay. So here is the model. You have these n fermions. Capital N is even in this talk. Okay, and because I'll be working with n upon 2 quite a bit. And so these are just the anti-commutation relations, and you would have recognized that these are nothing but just gamma matrices. And the dimension of the Hilbert space over here is 2 to the power of capital N upon 2. And this is the Hamiltonian which I was referring to. So it's we are working with just a 4 fermion interaction. You can, in principle, have any number of fermion interactions, okay? And there are very interesting consequences of increasing the number of fermions, but I will not talk about that now. Now, in principle, this is a Hermitian Hamiltonian, so we have a unitary quantum mechanics. But given of the order of n to the 4 couplings, it will be very difficult to solve this problem. So what people do is they assume that this comes from some distribution, because at large n we know that this model self-averages, and this distribution is chosen to be Gaussian, and this is the 2-point function, and this variance is 0. Okay, so this is the definition of the SYK model, and so let me tell you a few things about this model which are very useful for us. So firstly, that there exists an infrared fixed point in this dynamics, and that infrared fixed point essentially leads to an infinite dimensional emergent symmetry. That symmetry essentially is related to these maps. So diff R1 means, differentiable functions on R1. So this is the map. And if you are working with Lorentzian signature in space-time, this map is diff S1 mod SL2R, and this is the Euclidean version of this map, which is diff S1 mod SL2R. Now, I cannot explain completely in any detail how this SL2R comes about, but essentially the point is that, yeah, how do I explain that? Point is basically that the diffeomorphism symmetry ultimately is broken when frequencies are increased to be near this frequency breaking scale, which is J. And in that case, the diffeomorphism symmetry is simply broken down to SL2R, and therefore we are working always on this quotient manifold over here. And these are the standard, if you are from particle physics, you know that these are like pions, Nambu-Goldstone modes of chiral symmetry breaking. Okay. Now, these low energy modes, their interaction is described by effective action, which is a Schwarzschild. It's a very complicated type of action because it is a higher time derivative over here, if you see, okay? And it took some time to learn how to sort of quantize and solve this type of model. I will not go into all of that. The most definitive paper on the quantization of this, yes?
Sorry, so
yeah.
I mean...
you can ask questions if you,
yeah.
I don't mind.
So initially you had the spin couplings were just completely random, right? They're chosen from some Gaussian.
Yes.
So I mean, then is there a unique ground state, or what is known about the, like there must be multiple ground states, right?
No.
I mean, you like typically it's like looks like a spin glass model where you have a large number of ground states.
In this model, which is not supersymmetric, okay, this model which I am describing, you have a unique ground state, but I mean, and you have a large number of, there is no degeneracy in the ground state. Yes, that's the important point. But there is a large number of levels which are finely spaced. Spaced means e to the minus n spacing. And this is the object that you want to really understand.
Okay, the low energy spectrum.
Low energy spectrum. So it's a pretty complicated thing. And this, this point is basically encapsulated in this statement. This is the density of states actually. That e to the n upon n times s naught, where s naught is some number. That number is very important actually. So the point is that the spectrum of the SYK model is organized as follows. So you have these very, very low-lying modes, okay? There is no gap, and these levels are separated by e to the minus n. So there are e to the n of them in some sense. And then there are, excitations with finite gaps actually all over. But those I'm not interested in at the moment because I'm interested in looking at very low temperature physics and low temperature black holes and their evaporation. I'll tell you what it has all to do with black holes, but this is an important question that the spectrum is very complicated. So I mean, just let me just draw the spectrum for you. So it's something like this. And the gap is like this, somewhere up till here, and then there are levels like this. So we are interested in understanding the physics of this. And the dynamical degrees of freedom, which describe this part of the spectrum, are these maps. SL2R is the special linear group in 2 dimensions. There are many students here. Maybe I should be very precise about what I say. That's what it is. Okay. Did you get it? No. So you see, the point is f of t is like a hydrodynamic mode. See, what you want to do is that you have this very complicated system and you want to describe it at very long wavelengths. And so there is an emergent hydrodynamic mode, and that's f of t. And the hydrodynamic equations are given by the Schwarzschild, basically. That's the point. It's different from Newton's physics because the Schwarzschild has 3 derivatives of time. So learning how to quantize this was not easy, but can be done. So I was saying that there's a very definitive paper, final paper by Witten and Stanford, which actually told us how to really compute this path integral in a very precise and exact way. But before that, people knew more or less all the physics answers, so yeah. So please interrupt me whenever you like, because I like to have some feedback from, yeah. Yes. Yes. Yes, for large n, they form a continuum. And this is why the density of states is written in as a continuous formula. Yes, that is true. Yeah. Okay. All right, so then we have to approximate the SYK path integral. This is a long story, how it comes about to be just the quantization of the Shortian. Okay, it can be done. And from this path integral, you can derive, you can, for example, you can derive this very easily. The entropy is basically, if you calculate the free energy, you can find out the entropy, and the entropy turns out to be capital N times S naught, which is that number fixed for the SYK model, numerically computed, 0.46, etc., plus some term which is linear in temperature. Okay, this is very important. And then there is a fluctuation term, fluctuation around the saddle point of this path integral, which goes as the logarithm of the temperature. These are the, and now if you take a Laplace transform of this function, e to the minus x s of this function, you will essentially get this density of states. So this is the famous formula for the entropy of the SYK model at low temperatures, linear in T and a logarithmic correction. And from the condensed matter point of view, it means basically you have no quasi-particles. The whole model was invented to understand the absence of quasi-particles in a highly entangled quantum mechanical problem. So this is condensed matter physics. Okay. In my mind, there is no difference between all this condensed matter, gravity, everything same. All right, and why this model became very interesting for people working in black hole physics is this last equation actually. So if you compute, for example, and these computations are not easy, but can be done. They were done by Malasena, Stanford, and Kitaev. And you consider this so-called OTOC, or out of time ordered correlation function. It's a diagnostic of whether the system is chaotic or not. If you compute it in this model, you get this answer. There's an enhancement by J, and there is a Lyapunov exponent, which is just proportional to temperature. Okay. So Malasena, Stanford, Schenker proved a very beautiful theorem that for any unitary theory, this is the maximum value of the Lyapunov exponent under some assumptions. Every proof is under some assumptions. And this model saturates this bound. So this is the saturation of the Lyapunov bound by 2 pi upon beta. That alerts you that this model may be dual to a black hole in the bulk. That's the beginning. Any questions on this SYK model? Any? Okay. Let me now turn to gravity. Okay. So we are interested in understanding the physics of black holes. And for example, one simple class of black holes are black holes which are near extremal. Now, what does that mean actually? So in general relativity, you can have a black hole which has a, which has an electric charge. Far away, you will see that it has an electric charge. And when the black hole is extremal, the mass and the electric charge are almost equal. And we would like to understand the physics of the near extremal black hole. I don't want to go into this GR business at all, except to tell you that in a very precise way, you take this 4-dimensional near extremal black hole in 4 dimensions, and you learn to dimensionally reduce it. Why you want to reduce it? Because it's naturally getting reduced, because you want to understand the properties of the horizon of this black hole, of this 4-dimensional black hole. You don't want to worry about the singularity problem. That's another issue. But what is the physics and the dynamics of the horizon of black holes? And this, of course, has occupied the string theory community for now almost 2 decades or more. Yeah. So this is just a cartoon from this paper by Iliescu and Turiachi. This is a very recent paper, but this is the paper that completed this reduction very, very carefully and rigorously. So what is happening is that this is a cartoon of a black hole, okay? This is the horizon, the singularity is somewhere here. We don't bother about it. And very far, this is called the near extremal faraway solution. And this is a sort of a throat. The geometry is like a throat, okay? And the physics that I will describe now in an effective two-dimensional model is about this throat, okay? I just wanted to mention this to you so that you don't just go away home with thinking that we just work with two-dimensional physics. We are really interested in 4 dimensions. And this effective theory, when you zoom near the horizon of the black hole, is two-dimensional. And then that is dual in some sense to the SYK model, which enables us to do calculations. Okay. All right. So what is the theory of gravity in 2 dimensions, which I'm working with? So I should tell you what the gravitational theory is, right? So this gravitational theory is very simple. What happens when you dimensionally reduce it is that there is some number called phi naught, which is the value of the dilaton on the horizon. Dilaton is a scalar field, okay, just a scalar field that happens because of the dimensional reduction, times an integral over the scalar curvature like this. But this is a topological term actually in relativity. And then this is the action. So you have this scalar field multiplying r plus 2. And then there is a boundary term over here, which is what in general relativity people call the Gibbons-Hawking term. Okay, and this k over here is the extrinsic curvature of this manifold. So what we are doing is we have this ADS2, okay. ADS2, why? Because it's a, if you look at the variation of phi, you are working with metrics which are r plus 2 equal to 0. Negative curvature metrics. The simplest one is the Poincare disk or the plane. It's also called ADS2, anti-de Sitter space in 2 dimensions. Please don't worry about all these terminology, okay? Because this comes from some different subject. I don't want to sort of drown you in terminology, but this is the action of gravity. And what you want to really do over here is again compute the partition function. Integral over the metric and the dilaton. This is what we want to calculate. And you find that this partition function, when you calculate it, it turns out to be exactly the same as the SYK model. That's the point of the connection. Now, I cannot actually show you all of that in detail, okay? But the partition function of Cht gravity is in the low temperature limit is identical to the partition function of the SYK model. It gives rise to an entropy which is proportional to the temperature. And also there is a logarithmic correction. Okay, so if you look at this cartoon over here, the degrees of freedom over here are precisely these maps. Okay. And I just wanted to mention this, just like in the SYK model, you see that the degrees of freedom are identical. All the bulk degrees of freedom without matter, if the theory is without matter, just disappear. And all you have are on the boundary, these degrees of freedom. It also turns out that the action of this theory is precisely again given by the Schwarzschian, okay? And there's a cute formula actually which relates the Schwarzschian with the metric in the interior of the space-time. And this is a very simple formula. So for example, if you solve this equation, this is one of the very simple solutions, and you substitute this over here into this formula for the metric, you essentially get a Lorentzian black hole in ADS2. And similarly, if you are working in Euclidean time, you once again have the Euclidean equations of motion and the Euclidean maps, and that gives rise to a Euclidean black hole in ADS2. Is this clear? I mean, is there some question you have here? Because this, yes, by, yeah, Wick rotation. I mean, Lorentzian to Euclidean time is by, so basically you're basically then working with a Poincare disk, and the time is essentially going the boundary, and it goes from 0 to theta, which is the inverse temperature. Yeah. So, yeah. Good to have a course in general relativity for everybody. I wish I could smile. Okay, so this is the brief connection which I just wanted to make, and here are some drawings now about the space-time and how this solution looks in this space-time. And the key point is the following. Now, I just wanted to make a point. So if you, now that I told you that basically the degrees of freedom are curves on the boundary, right? These curves are basically parameterized by a x coordinate and a y coordinate. And the x coordinate is f of t, and the y coordinate near the boundary where z is very small is z times f dot. Okay, this is a very important equation. Okay? So for example, if you plot this solution over here and do the conformal rescaling, essentially this is the type of solution you have. And it defines a horizon. The horizon means at the time of this observer over here simply stops, and all the signals that emanate from here you cannot see. And that's what you mean by a horizon in this problem. So now, it's a very beautiful idea of, now I'm going to tell you a little bit about the work of Kurkulu and Maldacena, that they discovered a very simple order parameter to describe whether a space-time has a horizon or not. And here is the answer, that if there is a zero of this Jacobian t to f of t, then it signals the appearance of a horizon in the bulk. However, if this Jacobian f dot of t never has a zero, then the space-time has no horizon. And it's a very simple solution over here that illustrates this point I'm making. Incidentally, this is the classical solution that leads to, this is the black hole solution that leads to the linear temperature dependence of the entropy. Okay. This one, precisely this one. Okay, so is this clear? This is the key point actually about whether a space-time has a black hole or not. And if you want to talk of evaporation, at the end of the process, there should not be a horizon. And this is the point which I will try to explain in the rest of the talk, dynamically how it happens. Like hydrodynamic mode. It's not a dissipative mode up to this order. Up to leading order in J, it is not a dissipative. I use the word hydrodynamic because it describes just the long wavelength physics of this problem. Yeah, you may say that actually. Yeah. Okay, so this is a very important point, that whatever dynamics you have, whether you have a horizon or not, depends upon whether the time derivative of f of f hits a zero or not. All right, now, yeah. It has. Now I'm working with the Schwarzschild theory. I'm working with SYK model and gravity. They are identical at low energies and without matter. Right? Yeah. Absolutely. So what's happening? Pictorially, this OTOC calculation is a tour de force calculation. It's a very hard calculation. One summer student spent a whole summer trying to figure it out, and he almost went crazy. But then he told me that he was a different person after he understood it. So the point is that there is a 4-point scattering, right? Now, it is the exchange of this quantum of f of t. So what you do is essentially take a classical solution and plus write like this. And you can find out the Lagrangian of this fluctuation. It is when these fermions interact via this fluctuation, this low energy mode, that you have this exponential growth of the correlator in a certain regime, right? And all these experts, Lognagam students are sitting at the back, correct? So this is just the physics part of it. Absolutely. Related precisely to and the Schwarzschild mode plays a fundamental role there, actually. Without it, there's no such calculation. Yeah. All right. Okay. So let me continue now, because so now you see you have the SYK model. It describes a black hole, this very complicated object which has all these properties. So there's a horizon, it will always be there. How do you get rid of the horizon? What do you do? So what you do is you perturb this SYK model. And Kurkulu and Maldacena, KM, I'll say in short throughout the talk, found a certain perturbation of the SYK model, okay? A certain perturbation which is, from the viewpoint of the infrared fixed point, a relevant perturbation, okay? All right? Because it has two fermions over here. Okay, so if you compute the dimension of this operator, it is 1/4 plus 1/4, which is less than 1. It's a relevant operator. So you add this relevant operator with a certain small coefficient to the SYK Hamiltonian. The coefficient is small because otherwise it will drive you away from the infrared fixed point, and all of this description doesn't make sense then. Okay. So they found this, and they were able to explain the phenomenon of how you can get rid of the horizon of the black hole by a perturbation like this. Now, what does this perturbation physically do? I'll just tell you in words. It's like basically, so you have a horizon and you have a black hole with a mass. So what do you want to do? You want to suck that energy out, right? You want to remove the energy. You want to reduce the mass of the black hole. And this is the operator that does that, actually, physically. So from the viewpoint of the gravity theory, you're turning on a perturbation on the boundary, which essentially, behaves like a, refrigerator or anti-refrigerator. It simply pulls out the energy from the bulk. And if you pull out the energy, then the horizon goes away. This is just talking qualitatively. That's what this operator does, actually. Yeah. Yes, yeah, precisely, very good point, because this perturbation is small, it's controlled, yeah. That's right. Otherwise, you have to resolve the whole problem, and I don't know where you go then. Okay. So, sorry, how am I doing for time? I'm sorry. So what is you have a, is this a Russian seminar or what? Thank you. All right, so so now let me explain this theory of Kurkulu and Malasena a little bit more. So over here, for example, this operator has numbers only. Yeah? And what are these numbers? Now let me explain this to you. So now I want to explain to you a little bit about the Hilbert space in the ultraviolet of the SYK model. And it's the following. So what you do is you recognize that this operator Sk squares to 1. And in fact, these are all commuting operators for different Ks. And they can be simultaneously diagonalized. And their eigenstates are precisely these values of S square is 1, so Sk is equal to plus or minus 1. And we can just choose these to be normalized. You know, you can think in terms of you know, gamma matrices and constituent Pauli matrices, and all that can be understood in a very simple way. But I just wanted to give you a broad idea. So these states basically span the Hilbert space, okay, because they're orthonormal states. Now, there is a very important thing you realize about this space is that there is an operator that does the following. It takes the odd fermions to themselves and flips the sign of the even fermions. So this is called a flip operator. In fact, this is a subgroup of the orthogonal group, which is really operative over here because you are working with n real fermions. So there is a ON lurking in the background. And you can actually find a simple representation of this type of operator, which does this flip job on the fermions. The odd ones are left invariant, the even ones, the sign changes, and therefore the spin also changes. Okay, so with this simple preliminary, let us consider a state which is this BS state. So BS state means what? It means a state like this. You know, there are n positions over here. So you go plus, plus, minus, minus, plus, 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 minus. Right? Another one can be minus, plus, minus, 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 plus, 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 etc. Right? All of these are states which, in short, I'm calling BS. Okay. Now you can show actually by a calculation that these states, the BS states which I'm talking about, are all very high energy states in the SYK model. Okay, you can show that. So what you want is essentially a low energy projection of this state. So what do, you basically you know, take the SYK Hamiltonian, multiply by e to the L times h, and let L be very, very large. You know. So basically you project onto low energies. And these are the states of interest for our talk. Now, why are these states very interesting? Because, and this I think is a very important point made by Kurkulu and Malasena, that this state, which is made up of the microstates of the SYK model, is a candidate black hole microstate. This is a very important point for this whole work, or many other works. That this, so, you know, I mean, in more complicated models, we have no idea what is a candidate black hole state in terms of microstates. What are the microstates? We don't know. But here in this simple model, I can have an explicit formula for this black hole microstate. So now let me justify why this state of the SYK model represents a black hole in the long wavelength. Okay, so One reason in support of this proposal is that flip invariant operators, for example, like this 2-point function, appear to be thermalized for any choice of BSL at large n. Okay, this is a fundamental equation over here. That take the expectation value of any flip invariant operator, all the standard ones we work with in thermodynamics, for example, which are bilinears, and therefore are flip invariant. Their expectation values in this special state is the thermal average, and as or more important, this right-hand side is independent of which state you started with. Whichever way, whichever microstates you use to describe the black hole, they always give the same thermodynamics. Of course, this rings a bell right away, right? In whichever way a black hole is made, the thermodynamics doesn't see that, it doesn't care for it. So for all correlation functions of the standard type which are invariant under this flip symmetry, the statistical physics of all those operators is simply given by the expectation value in these special states and is independent of which state you started with. Okay. Yeah. I don't know whether it is ETH. I know what you mean, but I mean, eigenstate thermalization, but these are not eigenvalues of the Hamiltonian. There's a big, yeah, sorry. Oh yes, maximal, it's yeah, yes. Exactly, it's a highly entangled state actually, because the Hamiltonian is very complicated. Yes, because L is very large. Yeah. So this is not energy eigenstates. Yeah, right. So it looks like ETH, but it's a bit different. And also, this is an exact statement. Huh? I mean, this is, you can prove this. It's true for large n, this statement, what I said. Okay. All right. My God, I'm just doing preliminaries here for you. Of course, a very important question is that if you take any linear combination of these states, is it true that linear combination of microstates still represent black holes? We don't know at the moment, but some work we are doing in connection with that. All right. Yes? It's any operator. Like I wrote those bilocal operator, no? What does that mean? It can be local in time, but it can be non-local in the fermions, no? I mean, in the sense that psi at time t, ith component, psi at time 0, ith component, 1 plus 2, all of them summed over, is a flip invariant operator. So it can be very complicated set of operators. There is no locality, nothing there. Only flip invariance is used to prove this.
So it has this property, and but how do you say that you identify this with the black hole microstates that you're going to show now?
Yeah. I mean, right. So one point in our favor is the fact that these states act like thermal states, but not for all operators, and that's the main point. Certain operators can see these fellows, and those are precisely the Kurkulu-Maldacena operators. So they don't thermalize. Okay. So there's a lot of literature over here, a lot of things you have to prove. So I can't really do that over here. It may take a course to do that. But I just wanted to write down for you that this is the operator, a certain operator that we will consider of this type, all right? And there's a statement you have to prove then. What is the low energy? What is the low energy formula for the expectation value of such an operator in the BSL states? Okay, this is a calculation you have to do. And at large n, this is the answer, that if this state has a spin s, and if this operator has a spin s prime, then you just get the scalar product of s dot s prime times the thermal Green's function square evaluated at t minus IL at this complex value. In this subject, you work with real and imaginary time, and one point is in the imaginary axis, the other point.
Can I ask a question?
Yes.
Yeah, I'm actually super confused about how did you said like how did you generate these low energy states? I mean, it doesn't. I mean, I'm not sure actually how.
Okay. Okay. No. I'll tell you actually here. See, look at this definition. Okay. This is a high energy state that you can show if you compute expectation value of Hamiltonian, it's almost near zero. So that's high energy actually, measured from below. So if you look at this, this is an exponential, no? Exponential of minus L times a Hermitian Hamiltonian. And if L is large, this is a very strong damping factor, right? It projects onto the low energy states. That's why it is low energy. Is that clear?
And yeah, and you are now using this L as some kind of complex time.
No, twice L is just the inverse temperature, low temperature. So inverse temperature is large, so L is large. Right?
Okay. Okay.
All right. Okay. So, oh God, I'm running out. All right. Yes. This is not a flip invariant operator. Yes, previous slide. Yes. Yes. Slowest evolving, means what is the meaning of that statement? If you take this low energy state, yes, I agree with you. E to the IET, right? Yeah, but in this model which I'm talking about, as of now, there is no dissipation. So the use of the word hydrodynamic in that sense. Yeah, that's right. Yes, that's right. That's right. Yeah. Long wavelength, right? And I think this is a important little lemma that you establish in this subject. This has been done in some of our papers in the past in a very sort of so this statement that this expectation value just gives the square of the thermal Green's function. And then you have to learn how to compute the thermal Green's function at low energies. And this is the answer. Okay? This is a very important equation. All right. And then what we do is, because F dot is supposed to be positive or zero, we parameterize it in terms of this so-called Liouville field. Okay? We call it Liouville because, well, for historical reasons. And therefore, the low energy large N expectation value of the Kurkulu-Maldacena type operator measures the spin of this state and is given by exponential of phi upon 2. Okay? So this is the infrared projection of those UV operators in these low energy states. Sorry. And similarly, you can consider a square of this operator, and it gives rise to this low energy object with a very, very important negative sign. Now, I'm not going to the proof of all this because you can see it, or you can ask later. So now I have given you all the background of the SYK model and the operators which I'm interested in working with, which are capable of removing energy from the system. And an operator which is removing energy from the system can also be made to add energy if you flip the sign. And this is something which we had done some time ago. Yeah. Yeah. Sure. Yes. See, yes, exactly. In the sense that they don't thermalize. That's the key point. They don't thermalize. So their expectation values cannot be calculated in the thermal ensemble. But then the results you wrote, the exact calculation without. So what happens basically is that the expectation value in this case turns out to be the square of the thermal Green's function. That's a calculation. Then you do others and you'll find some other objects actually. Okay. But these operators, yes. They are very, very different from typical operators. No. How do they? I mean, they are basically the sum of spins in some sense. Yeah, I mean, they are complicated in the sense that they don't have this flip symmetry and they don't thermalize. And they don't thermalize, and they have the possibility of being able to assess the microstates in the ultraviolet, these S states actually. That's a whole different discussion. I won't be doing that today, but those are these operators. No, I'm talking of ultraviolet in the sense of the SYK model. We don't know the gravitational interpretation of the SYK model when the temperature is very high. We don't know that. We don't know that. At least I don't know. So at low energies, we can match them. Okay. All right. Sorry. Okay, so now we set up the problem of radiation. So as you know that ADS2 essentially is some sort of a box, right? This is the boundary of the box, there's a black hole. If it radiates something, it will be reflected back from the box. I mean, this can be all made very precise, that black holes don't evaporate in ADS spacetimes. Because ADS is a very nice geometrical box. It has a boundary. Some radiation goes there, it's reflected back. So what do? You couple this to an external system. You couple it so that the radiation can escape into that system. Or you can discuss thermalization of the coupling when this system couples to this system. So this is what I want to do now. So what is this system that we work with? It's a system of n free scalar fields, nf scalar fields. And the coupling is very simple. It's instantaneous coupling in time. You take these type of operators and you couple to the scalar fields in this simple way. And after many trials, and this was in some sense something one found, that the complete evaporation of a black hole over here, when you couple to this system, is possible by this type of combination of Kurkulu-Maldacen operators. If you put G prime equal to 0, the black hole never evaporates completely. For reasons I don't understand all these things, but this is experimental math in some sense. So this is the operator we found to couple to the bath. And even then, these couplings over here are time independent at the moment. But we find that after a long period of time, something which we call Tmax, the low energy approximation starts breaking down because of fluctuations. And so then we quench these couplings again at some later time. I'll come to that briefly. Okay, so this is the model that we are working with. We have 2D gravity, and we have this bath over here, conformal field theory, and this is the SYK model interacting with this system. So now on, let's forget about 2D gravity because it's dual, so we work with the SYK model. And these are all cartoons of the same thing. Okay, so now we have to do a lot of calculations actually to find out what this effective Lagrangian is. So once again, which I told you a little bit before, that this expectation value for this linear combination of operators yields a function like this, e to the phi and e to the phi upon 2. So the interaction essentially at low energies turns out to be a linear combination of this type of operators coupled to the bath. And then of course you have the SYK model itself. So the full system of SYK interaction and the bath or the conformal field theory is sort of governed by this type of complicated action. Okay. Now what do you want to compute? You have two systems which are coupled. We discovered the operators which are needed to couple these two systems. And now we want to, what do we want to do now? We want to compute the initial density matrix and evolve it. Okay, so that's what we want to do. That's our job now, how to do the dynamics. So the initial density matrix is not very difficult to do. So this is what the initial density matrix is given by the tensor product of this matrix of the SYK model and this, and we want to evolve it. And these are pure states, therefore this is true. And we want to compute the expectation value of some operator at long times. All right, so all this is fine. So the density matrix for the SYK model is given in terms of this Mandal and S.R state, which represents a black hole. And the density matrix of the whole field theory can be calculated using Euclidean path integrals. Everybody knows I am going to work in that limit in which this is actually a squeeze state, which you might be familiar with from your work in many body physics. For me, the initial state of the bath is a squeeze state, which is characterized by a certain length, capital L, so that capital L times this dimensional scale is much, much greater than the inverse temperature times J. So this is important. You want a cooler system in some sense to interact with a hotter system. That's what this is. And so you construct this state. No, SYK is in this BSL state. BSL state. The BSL state, the one that I wrote down. No, BSL. Yes. Exactly. This one. Exactly. Yeah. You'll see. Yeah, it's even lower temperature and it is massless, so it will induce long-range correlations in the open quantum system. I'll come to this. I mean, we are getting into the difficult part. Yeah.
Just one question. These BS state that you earlier talked about.
Yes.
Are they like eigenvectors of the Hamiltonian?
No.
SYK?
No, of course not. They are not energy eigenstates. That was the thing that we discussed before.
Okay.
Answer is no. You can check.
So one thing is like what does this L is it like what values does it take in the BSL?
Oh, it's just a real number, which
Or it's just a parameter that
it's just half the inverse temperature. That's what it is. Simple. Okay. No, the coupling is what I gave you. Now the question is whether it's consistent coupling or not. You'll see that this is the thing I want feedback on, that the strength of the coupling is weak. No, it's weak, but it's instantaneous. So I'll anticipate the problem is that ultimately when you do all this, you arrive at a third order in time differential equation, which reminds you of the radiation reaction type of problem. And so we are finding that there are certain solutions in the parameter space which are blowing up. And dissipation in the sense that there is a third derivative, first derivative in time. But yeah, I don't know how to say it. I mean, yes. But because we have coupled it to the bath, it doesn't bounce back. There is a flux of energy from ADS2 into the bath. That we can see also. I'll show you all. Yeah. Yes, in the SYK language, it will mean that this F dot, this dynamics spits out a certain value of F dot asymptotically, and it will not go to zero. And then, therefore, the dual geometry doesn't have a horizon. That's what we want to show. Let me come to the things I want some feedback on. Okay. So, all this is standard now. From now on, it's all standard, actually. You have this density matrix, and because it's a density matrix evolution, you need to do double contour. You go and come back, right? So you have two copies, the Schwinger-Keldysh formulation. I think all of you know all these things. So you're in statistical physics, so I don't want to belabor this point. And you simply integrate out the bath degrees of freedom. You arrive at this Feynman-Vernon influence functional, right? So this is the problem. These are the contour, the upper contour and the lower contour. The blue one is the bath. The orange one is the SYK model, and they're interacting by these lines over here. What you do is you want to integrate out the conformal field theory, okay? And you get this complicated open system of the SYK model. So you can do all these calculations. They are straightforward, tedious, but you can do them very correctly by introducing a ultraviolet cutoff for the conformal field theory and learn how to take the cutoff to infinity. Everything that I'm saying is pakka correct. And you arrive at a certain effective action, which is the Schwarzschian on the top contour, minus the Schwarzschian on the lower contour, minus, there's an I here, which naturally comes, and this is the effective functional that you derive when you integrate out the bath. And one important point is that I am not generating any additional terms to leading order in 1/j for the SYK model. The SYK model that I work with is still without dissipation. Okay. All right. You can do all this systematically. And then you do the so-called Keldysh rotation or fields, Keldysh, this very beautiful way of expressing this problem so that the full action can be now rewritten in terms of the Keldysh fields. And now what you do is the following, and this is the point. So we have this very complicated problem of two fields, path and all that. And now you can't solve all that. So let us do perturbation theory. So I want to do perturbation theory around this object, phi q equal to 0, so that the field in the upper and lower contour is the same. Perturbatively, I compute, I can do that, and I get a quadratic action over here and a linear term. The linear term gives the equations of motion. So all this is textbook material in Keldysh formulation. And the fluctuations essentially lead to a Langevin type equation, because I can take this object, this exponential, and rewrite it in terms of a fluctuating field, which is the noise. And if you take higher orders in 1 upon n, then this noise won't be Gaussian, and it'll have more complicated formulas, but I'm not going to do that. People have done that, like Lugnaigam and students have computed, not in this model, but in other models, the higher order corrections in which the noise is not Gaussian, which has nonlinear terms. But I'm not going to do that. I'm going to keep in large N just the quadratic term and rewrite this in terms of a Langevin type of noise. And this is the object that you arrive at. You arrive at a stochastic differential equation, which all of you would have expected because you are doing open quantum systems. And this is what it is. So this is the noise. This is the noise correlator. The noise correlator is not short-ranged. So this is not like Brownian motion. It's the highly non-Markovian system. And this type of stochastic differential equation is called a colored equation in the literature, because, well, never mind, because of this, actually. Yeah, right. Yeah, the noise correlation is non-trivial. There is a equation has an integral, a memory, it's not Markovian. So I don't know about this fluctuation dissipation theorem. I'll come to that actually if you have the time, that in certain situation, you can actually see the Einstein-Smoluchowski type of behavior in the fluctuations. But in the more complicated case, when the black hole evaporates, you don't see that type of thing, but something else. I'll just come to that later on. Yeah. Yeah. Yeah, Langevin type equation, right. Yes. Yes, 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 yes. I mean, the system is dissipating because it's pumping energy into the bath. Yes. This term, you mean? Yeah, you're right. So this term comes from the coupling to the bath, no? This is the term, right? This is the term which is, the good old SYK, black hole and all that. No, it's highly non-Markovian. So you can say there is a potential, but this is what it is. Yeah. It's not local in time. Yeah. But you see, usually there is an x dot term with a coefficient, and there is a noise term with a coefficient. And fluctuation dissipation essentially is a connection between these two coefficients. So this equation is very different, and I'm not sort of an expert in all this to be able to answer this type of question. I mean, what is the analog of that? I don't know really. Because ordinarily it's the damping term coefficient is related to the noise, right? That's the diffusion. Yes. Yeah. Slowly, yeah. That's right. Okay, let me move ahead. Okay, so this is our problem to solve this type of thing. It's quite difficult, I think, to do this now. There are lots of comments over here. The stochastic differential equation can be actually, recast as a local third order equation. This is just simple algebra. Okay, just take my word for it. And all the numerical work actually that was done for this model by, here he is. Any questions now about numerics, you ask him. Anurag, were done for this equation. Yes, of course, I took one more time derivative. And you can manipulate that it for this particular integral differential equation can be mapped into precisely. Yes, correlation has a derivative, sure, certainly. Yeah. Okay, now you might ask why one does this. Apparently, I'm not sure of this, but I was told that the numerics is easier this way. But there may be pathologies in trying to do, I'm told by, we had a talk in our group. So Loganagam and Subrat felt that perhaps third order equations numerically, if you try to solve them, accumulate errors that lead to runaway solutions. I don't know all these very well, but I just want to present what we have done. So there's a control space of two parameters, right? G and G prime. Now there is a part of that control space in which you have very well-defined good solutions. But if you go outside of that, there are blowing up solutions, and we'd like to understand why they are blowing up. Numerically, solving the third order equation. Maybe that's the wrong thing to do. I don't know. Let's, sorry. Yes. Yes, I agree with you. No, I agree with, I understand what you're saying. Right. Right. More difficult problem, perhaps. But the pathology which I was referring to happens when the noise is set equal to 0 in the classical part. Now, just 1 minute. I just want to. Okay, so this is the problem we like to solve. Now we do something which may not be kosher. I want to take this SDE and do one more perturbation theory over here. I want to do an expansion of this field in terms of phi. Don't mistake it with the phi that we started with, the Louisville field. This is just a different notation. Times 1 upon root n times a fluctuation, okay? So then the equation that we had splits into two parts. This is the classical part, and this is the fluctuation part. So this is basically a linear operator on C, and you have to solve that after you solve this equation. So you solve the first equation, find the solution, substitute in the second equation, and find out the fluctuation of C. This is the equation of stochasticity, really. The first is a mean field equation. Okay, now at this point, you just do the numerics, and we did, not we, Anurag. And he found 3 classes of solutions, and this is the point I want to make to you. There are 3 classes of solutions, depending on where the control parameters are. Let me just show this to you. So this is the G axis, and this is the G prime axis. These are our 2 control parameters, or coupling constants, sorry. Control parameters in engineering terminology. So one finds, and by doing all this work, that there is a region over here in which the classical equation has well-defined solutions, okay? And those solutions are divided into two parts. One, this red part, when the control parameters are in this region, if you choose a point here and solve the problem, then the black hole does not evaporate, but it becomes a smaller black hole asymptotically with a smaller mass and a lower temperature. But outside this region over here, outside this dotted line, the solution simply blows up. I'll come to that at the end. So now let me try to focus on this region. We are lucky that there is a region, a non-zero region, in which you have meaningful solutions. Okay, so very quickly I will look at the solution in the red region. You essentially find that the phi goes, you can see it from the graph over here, for large times as minus a constant times t, which means that f dot essentially goes to 0. Therefore, you're still left with a black hole. You can compute the asymptotic state's black hole temperature and its mass, and it's all fine. So, you have a good solution, smaller black hole, doesn't evaporate completely. Good, it's a good result. Consistent, physically consistent result. The solutions in the green region are more complex. What happens basically is that the solution in the green region stabilizes into an oscillation around some fixed value, which we can determine. Okay. So this is how the solution looks like. So what we did basically is we analyzed this part of the solution where there are oscillations analytically. Okay. So the late time solutions are around this. So we were prompted or guided to do the theory by the numerics. So this is this particular line, which we get by setting f prime, that function f prime equal to 0. Whatever it is, do perturbation theory around it, and you find essentially an equation which is very familiar, which is the Airy's equation, or I think the equation has some other name, but the solutions are due to Airy. So, it's solved in, Airy function, right? But the equation has somebody else's name, actually, I forget now. Anurag, do you remember? Okay, we should give credit to the guy who discovered it also. So anyway, so this is the solution of the Airy function. You have to choose these solutions, okay? Airy functions have lots of other solutions. These oscillating solutions. And then you find that these oscillations, as time goes on, grow very, very large, okay? So this is like, the frequency, for example, you can read off from these equations over here very nicely. This is just a harmonic oscillator type equation. And the frequency is given by this formula. So as time grows, this frequency actually becomes larger and larger. And then there's a problem with our low energy approximation. All of this was done assuming that omega was much, much less than j. I put j equal to 1 in this, okay? So there must be a certain time scale this equation gives you, beyond which your coupling to the bath, that whole theory is no good, because you are moving out of the domain of your approximations. Okay, so there is a Tmax, and this Tmax is there. So beyond Tmax, we make, so what we do is basically, we do decoupling of the bath by functions which fall like this. So this is all dictated by the analytic calculations and the numerics, that you switch off the bath, but they switch off the bath in a very specific way in order to stay within the low energy approximation. It's fine. The important thing is that by this time, the black hole has actually evaporated. Okay. And what happens basically is that you find a new solution asymptotically, which is an oscillatory solution for f dot. So this F dot is always positive. It never goes to zero. So you find a solution in which the dual geometry doesn't have a horizon. And so the black hole has evaporated. There is a region of parameter space in which, a good region in which this is true. And what you do is basically you take this quenched couplings and resolve the full problem consistently, and you find essentially the same type of answer with the oscillation. But now the oscillations are in good control. And what, in a sense, is really happening is that if you take this equation, full equation that we are trying to solve, you can define, as time t becomes larger and larger, this effective potential sort of can be replaced by its asymptotic value. So this is a little, I'm going a bit fast, but let me, in pictures it's like this, that the effective potential firstly comes and cuts the real axis, it forms a certain, it goes below the real axis so that it comes like this and goes. So there's a well. Then as time goes on more and more, this is what happens. Then finally it stabilizes into this effective potential, which is given by this formula. And so that's what's happening really, that the effective potential cuts the real axis and has a well. And once you're in the well, the particle essentially just keeps on oscillating. And if it oscillates, the value of the function can never go to zero. And therefore, this is the sort of a very physical way of saying why the horizon has sort of gone. Okay, and then, you can, yes. Yes. Yeah. Exactly. So what's happening is that we are estimating the third term. This g of t and g prime of t essentially go as 1 upon root t. So now you take that whole object, and what you find essentially is that as t becomes large, this you can actually see quite easily from the solutions that the potential basically starts going deeper and deeper. If you didn't put the quench, the potential will simply go deeper and deeper and deeper and deeper. And then those oscillations are very strong. So you cut them off by this type of trick, because coupling to the bath is in your hands. And once you do that, then you find that finally the potential really stabilizes. And you have a system actually which is a very simple system whose end state of the dynamics is the fact that F dot never hits a zero, and so the horizon is gone. Okay, so this is almost towards the end now. You have this complicated equation. So we invented a function, this is a non-equilibrium system, so energy is really not conserved. So, however, you can invent so-called energy, this is the conserved part when the bath is not coupled, but include this term, and you find a very nice inequality that the time rate of change of this object is strictly negative or zero. This equation actually helped us a lot in trying to figure out a lot of things over here, because it is a very definitive sign. If the sign was fluctuating, it wouldn't have guided our eyes to find the right solutions. But nevertheless, you plot this. So you see the energy is this object just is going to zero and stabilizes at the bottom of the potential. Okay. So just take 5 more minutes. Is that okay? So this is an example of a blowing up solution, you see. So yeah, so if you choose G and G prime outside the green and red regions, then you have solutions like this, and we don't understand why this type of phenomena happens. We don't understand. Is there something wrong with the coupling? I mean, one suggestion is that there should be a delayed time coupling. Means the SYK model, the bath reacts a slightly later time in the coupling. So this is one suggestion due to Lognagam. Suvrat has a suggestion that one should redefine the third time derivative in a certain way, in which in the past there was some work in which third order equations have good solutions. So we don't know. I just wanted to flash this. And if you have any thoughts, please let us know. So all this song and dance on the SYK model, pretty complicated stuff. What is the geometrical? I just give you this picture that what we are looking at essentially is the fact that this is a black hole because this curve, this red curve, actually ends over here, and there is a horizon, and the solutions we are finding for the curve are like this, and so this f dot never hits a zero, and so any radiation from here, there's no horizon, so you can just see everything behind the horizon that was. But you have to be a little careful because the concept of horizon is only asymptotically defined. So all that can be taken care of. I just wanted to note of caution. Okay, so of course I don't want to continue with the talk, but we take these solutions and we put in the fluctuation equations. And when you have the case in which the black hole asymptotically becomes a smaller black hole, then the fluctuation, the 2-point function at coincident times, the psi square expectation value, has this very nice form actually. And this form essentially is, like the Einstein type of equation, Einstein-Smoluchowski. The diffusion equation is like this, and this is the temperature over here. Okay, so something which you expect has happened. On the other hand, if you look at the case of GG prime in the green region, then the solution is of the coincident fluctuations is very fluctuating over here. And you plot it versus time, you don't find this very simple relation of Einstein, but this type of a plot. So there is a difference between the fully evaporated and the asymptotic state being a smaller black hole. All right, so the temperature dependence at fixed time is not linear like in the Einstein relation. Okay, so I think I'm more or less at the end. Calculated the dynamics of black hole evaporation or dissipation in the SYK model. That is holographic to JT gravity, which is a dimensional reduction of 4-dimensional near extremal black holes. And this model to study the dissipation of the black hole is coupled to a bath of NF scalar fields with appropriate sizes taken into account all over the place so that all our calculations are valid. We were able to do a calculation and essentially understand how a horizon sort of disappears in a dynamical way. But we need to understand still the part of the parameter space where the solutions are blowing up. So this has to be understood. And the last thing is, of course, how universal is all this that I talked about? I think it's likely to be pretty universal for all near extremal black holes in any dimension. That they will all be controlled by the SYK model and its low energy dynamics. And so, thank you. Sorry for the long time, but yeah. Do you have any question? Yeah. Right. SYK. Yeah. Yes, exactly. Huh.
So like,
Exactly. Okay, good question. Oh yeah, so what you do is the following. So you will have to, for example, if you want to compute the purification, for example, rho square is involved, right? Rho square means essentially you'll have 4 contours, right? In the standard Keldysh type of calculation. So that can be done. How to join up the contours we have learned recently. And what you get essentially is a different differential equation. That means a different saddle point. You get a new saddle point to compute trace rho square, which is the one you are asking whether this trace rho square or those things will satisfy the page curve. Yeah, which is exactly what I'm saying, that the saddle point and the field configurations we are using to compute the evaporation cannot compute the purification. You need, there's a different saddle point. And that's apparently that's sort of expected, that the saddle point is different. Oh yeah, because we are working in a unitary setup. Yeah. Yes, right. But we have to calculate those things, and yeah, I think all these calculations people have done are, you know, in simpler models, and there's a lot of hand waving. There's no real dynamical calculation of the page curve, right?
any questions from people online? Okay, so
if you
thanks
could
a lot.
explain, just if you could explain the quenching part, I didn't fully understand this. Like, you basically reduce the coupling to 0. That's what you said, right?
Yes, but in a very specific way, to going to 0 as 1 upon square root of t. So a certain remnant is left because the fields are growing in such a way that if the quenching is done in this particular way, then you have a resulting effective potential which is not trivial.
The divergence.
Yes. Give
But why do we want to, again, why do we want to remove the coupling? Is that?
The reason is the following, that if you let the system as is carry on in time, then the oscillations of the solution are so fast that you are outside the realm of the low energy approximation, because our entire theory assumes that this omega, the frequency, is much less than the scale of the SYK model.
In the low energy states, the BSL states, is that?
Exactly, okay. Exactly. So the discussion in terms of the low energy modes f of t will break down if your spectrum contains high energy modes. That's why you need to quench it. You need to decouple the system.
So the first equation that you wrote down, that BSL equals to in terms of BSL in terms of these BS states, right?
Yes.
That was the approximation. Is that what you're saying? Or was that exact?
No, so I didn't quite understand. See, the point is that what are we doing? What we are doing is we are working in a certain approximation of the SYK model in which the frequencies involved in the time evolution are much smaller than the intrinsic scale of the SYK model, which is given by this dimensional object J, which is dimension of inverse time. Now, It is this that enables us to locate an infrared fixed point. It is this that enabled us to see that that fixed point has an emergent infinite dimensional symmetry. Then we learned how to go a little bit away from that fixed point to break that symmetry. And the symmetry is broken precisely by the Schwarzschild action. The Schwarzschild action is representing the breakdown of that diffeomorphism symmetry to SL2R. That's why the Schwarzschild action is proportional to J. I'm sorry, inverse of J, n upon J. And so as J goes to infinity, I mean, just completely low energies, you had the infrared fixed point, there's no Schwarzschild, there's nothing. So we are working in this type of approximation. And when we look at the solutions in the coupling to the bath, you find that these solutions are oscillating very fast. So what do? I change my coupling, the way I couple to the bath, just to save my model. I mean, ultimately, we were just working to, repair broken solutions. That's the way to do it. I mean, I don't have a real theory as to why I should be doing this. I was doing it to be able to get a consistent theory of evaporation. Does it answer your question?
Yeah, thank you.
It'll probably just touch.